This conference will now be recorded.
So good morning, everyone. And welcome to a fresh new session of mathematical economics classes. And today, being the first session, what we'll be doing is we'll try to first create out a blueprint of the syllabus that we have. Right? So, how are the different topics that we have with us is related with each other? That is something that we want to understand, right? So, so there are two broad areas, right, on which the mathematical economics syllabus is built. So what are so rather what is that broad area? One of them is the optimization. One of them is optimization. Now within optimization, you will have multiple subclasses, right? And you have different topics and subtopics or frameworks. Right. And the second that you have, the second topic that we have over here is the real analysis. Real. Now, when I talk about these two topics, right, now there is obviously some interdependence between each of these two topics. Right, so there is some kind of an interdependence. And what causes this interdependence, or what is the reason of this interdependence? The reason of the interdependence is that this optimization and real analysis both are built on the assumptions of the real variable. It's based on is based on the variable being a real variable. Now the question that comes out over here is that what exactly is a real variable? Now, a real variable is a variable which can be defined over the real space. So, if I have a 2 cross 2 Cartesian space, I should be able to plot that point on that real space, right? So it's like a very simple graph, or if you think about a real line, I should be able to put plot a number on that space. So, any number which can be plotted on that space is a real space. I mean, is a real variable, right? Okay. Now the next question which comes out over here is that then how is it that your syllabus is structured? And let's first look into that, right? And that's the most important part. And do correct me if if I am going outside your syllabus sometimes. So have the syllabus open in front of you as well. Okay. Now this optimization part is first divided into two broad groups. First is a static optimization. It's a static optimization. And the second that I have over here is the dynamic optimization. Is a dynamic optimization. Now, the static optimization is the more conventional optimization models that we work with, right? So you have mean, median, you have the first order condition, second order condition, and you have the concept function, limits, continuity, differentiability. You have concave optimization process. You do the Lagrange and all these things, right? So these are your very known methods, right? Because you are optimizing a set of variables at a given point of time. And the second set of optimization that you have is dynamic optimization. So where you are actually optimizing a series, or you are trying to optimize a set of variable a function over a period of time, right? So that is what dynamic optimization is. Now, one very important characteristic of the static and dynamic optimization is that they fall under a specific type of optimization. So they are optimizations under uncertainty. So they are nothing but optimization under certainty. Under certainty. Now, there is always an element of certainty where optimization under certainty. Now, if there is an optimization under certainty, the second set of optimization that we need to focus on is optimization under uncertainty. And this is where you talk about the uncertainty theory. So this is where you have your optimization under under uncertainty. Right? So this is your uncertainty theory. Now, when you have done a whole optimization exercise, right, why would you do an optimization exercise? To reach to an equilibrium, right? To reach to a best possible obtainable value, or to reach to a best possible situation. That is why you are optimizing. Let's say you want to maximize your utility or minimize your cost, or you want to do some of these exercises. So the way you go ahead is you try to optimize them, right? So, and while you optimize it, what you are doing is, given a set of constants, you are trying to reach to a best possible state that you can. But the question that comes out over here is to understand that whether is that state attainable. If it is attainable, is it sustainable? And for doing this, you need to analyze the state of the equilibrium that you have obtained as a result of an optimization process. And that is where the last part of your syllabus comes in, where you talk about eigenvalues, you talk about eigenvectors, you talk about phase diagrams, and you try to qualitatively assess that equilibrium that you have obtained as a part of your optimization exercise. So That becomes the second part of your syllabus. So the first part, you are trying to understand the principles related to optimization, optimization under different circumstances. That is, you're trying to understand the static optimization, which is optimizing a problem or optimizing a set a variable at a given point of time. Then you are going for dynamic optimization, where you are trying to optimize a variable over a period of time. Then you are trying to understand optimization from the uncertainty perspective. And finally, what you are trying to do is you are trying to understand optimization under uncertainty. That if there is, so if there is a lottery, then how do I go about getting the so optimizing my behavior, optimizing my choices, right? And then encompassing or covering up all these is your real analysis, because the variables with which you are working is real. So obviously the graph or the Cartesian plane on which you are plotting the points to reach your optimum point, you're plotting your phase diagram, will have certain characteristics. So those characteristics is something which is explained by this particular real analysis. So it's explained by real analysis. So real analysis is the foundation on which the dynamic or the static optimization stands, right? So very much like in a house, when you're building a when there is a building construction going on, you cannot see the base because that's deep down, right? And on top of that, the building stands. All you can see is the building, but the strength of the building is determined by the soundness of the base, right? So similarly, real analysis over here is that base. That is why you often do not see a direct application of real analysis in the real world. So because that is based on a lot of other theoretical, so very abstract theoretical concepts. But yes, when you are trying to frame an optimization problem, at the underneath, right, at the beneath that entire framework lies the principles of real analysis, and it is those principles that you need to explore, right? So first of all, before we start off with it, right? So let us start off with understanding this relationship between the real analysis that you do as a separate paper and the optimization that you do as a separate paper. So let's try to understand the relationship between the two, right? And how do they build into each other. Now, once you have understood that, then the next steps become easier. Now, before we go on, but before we move on, right? So we'll start off from a very basic concept which you had already done. So I'll start off with the consumer's optimization problem, right? And we'll use that example to associate between or to develop the relationship between this optimization frameworks and the the real variable, right? The real analysis, the real variable, and so on. So let's try to understand now. Now you started off when you started off your economics classes, right, at the very, if you go back to the graduation days, you started off with something called a consumer's behavior, right? In a consumer's behavior, in a consumer's behavior, so you had a consumer who had an income, and there were these market prices, and you're trying to understand that what is the point where he optimizes or reaches his point of maximum utility. So over there, the consumer was actually facing a optimization problem between the the prices of the goods, the assets, and the uh, the the graph. I mean, his income and choices. So between the commodities and the financial reality. And the question that we always ask ourselves is that what is that highest possible utility curve or the indifference curve can this consumer attain, given that he has this prices and this income facing himself. So that is something that you need to develop, as a part of this. So that is what we want need to develop as a part of this static optimization. We need to develop that framework which leads us to that optimum or the maximum utility, maximum possible utility. Right. So we need to develop that algorithm. We need to develop that framework. Now, once you have reached there, so, and now to reach to that point of optimization, you had multiple assumptions coming in, right? Multiple situations or multiple necessary conditions which you believe should be there for that equilibrium to be attained. And you saw that whenever one such condition was removed, right? One such condition was removed from the model specifications, you would see that the results would totally change, right? So before we start off with optimization, right, we will start off from this by exploring this simple example of consumer's behavior. We'll explore the assumptions, and from there we'll develop that relationship between real analysis, static and optimization frameworks, right? So that's the part that we'll first start off with. Now, this will give you an idea as to why is it that your syllabus is structured like this? Why is it that you are being taught all these things? Only once you are sure of that, can you go ahead and you can explore each of the topics. So we will start it from there. Clear? Okay, I'll take a pause over here and I'll take up questions if there are any. So I have a question from Orno. Orno asks, what is the definition of dynamic optimization? So dynamic optimization is nothing or no, but it is an optimization over a period of time. So where you are not optimizing it today, tomorrow separately, but you are optimizing it continuously over today and tomorrow. Right. So that is what dynamic optimization is. Okay. Now Shoma has a question that definition of real variable. So a real variable is a variable which can be plotted on a real space. If I draw a real line, so any number which is lying in the interval between minus infinity to plus infinity is a real number, right? So what are the properties of a real number? So if you take a square root of a real number, you will get back a real number, right? So let's say if you take a root of -1, now the root of -1 is what? So is an imaginary number set, right? So they have to be plotted on the Argand plane. But a real number is a number, or it's a number which has a positive decimal portion associated with it. You can take a proper square root. You can perform any real number mathematical operations on this. And what you can also do is you can plot that on the real space. So when I say the real space, what I mean is a two-dimensional real space, which is your Cartesian plane. The Cartesian plane is nothing but that graph, that the plane that you use while you are plotting any graph, the x-axis, y-axis together. So that's the positive quadrant of the uh, Cartesian space. So any points, any number which you can plot on the Cartesian space is nothing but a real number, right? And the variable which takes a real number is a real variable. So x belongs to real numbers is a real variable. Okay, any other question? Okay, fine. So let us start off with that example on consumer behavior. Right. Okay. So how does the consumer, what exactly is the objective of a consumer? Right. So the consumer wants to maximize his utility. And how does he do that? So the optimization problem that we talk about is max u is equal to u xy subject to px into x plus py into y is equal to m. Right. So this is what the optimization problem of the consumer is. So the consumer would always want to maximize his utility subject to the prices and the money income. So therefore, given that the consumer tries to, so given that the consumer tries to optimize his utility or is trying to optimize his utility and he has two commodities in place, right? So he has two commodities from which to he chooses, right? Now this consumer is optimizing at that given instant of time. He's not thinking over the next 10 years or the next 15 years or the next 3 months or 4 months. He's just thinking about that instant of time. So therefore, this example is a typical example of a static optimization. Now the question is that that how is it that this optimization is happening over here? Right. So over here, if you think, if you see a series, you can say that what I'm trying to do is I'm trying to first I plot a indifference curve, and then I have the budget line, and then what I do is I look into the tangency between the two. So now the question is, why is it like that, right? So what is going around? So first of all, let's try to plot this graph, right? So let's try to plot this utility function. Now, now if I talk about this utility function, so which is your u is equal to u x y is equal to u x y. So what is it that you are planning to do? What you are planning to do is you are trying to plot a space over here, right? So you are trying to plot a space over here. You have a 0, you have a x, and you have a y, right? So 0x is nothing but your units of good x, of x, the units of y. You have the units of x and you have the units of y. Now, if you think about it like this, what you will see is, so this is some units of y and this is some units of x. So every point in this two-dimensional space is a combination of x and y. So what is this xy combination called? X comma y. This x comma y combination is called a Cartesian product. So a Cartesian product is a case, or it's a product where you have, or it's a combination of x and y, where you have x being obtained from the x variable, the first element of this being obtained from x, and the second element being obtained from y. And this is known as a Cartesian product. And the question that comes out over here is that what are the properties of x and y? The properties of x and y is that x can be greater than equal to 0 and y should also be greater than equal to 0. In other words, both your x and y must belong to real number. So x in the Cartesian product belongs to the set x, right? Where and y belongs to the set y, where both x and y belongs to real number. The x belongs to real number and y belongs to real number. So one thing that you can see over here is that before you go to optimize anything or do anything, right, you first must go ahead and define the nature of the variables, and that is where these variables are real variables, and that is where the analysis of these variables will be called your real analysis. So that's why I said that when I began the discussion that that this so where I began the discussion is that these uh you know so these Cartesian products are so this entire optimization exercise, before even I go for the optimization exercise, right, it is very important to first understand the properties of the variables, and that this real analysis is that foundation which helps us analyze the properties of the variable and the properties of the spaces where these variables are plotted. So if you look into this 2 cross 2 Cartesian plane, so this plane that you can see over here, this the plane between the two axes. If you have a look into this 2 cross 2 plane, the 2 cross 2 plane, that 2 cross 2 plane is called the Cartesian plane. Is called the Cartesian plane. So this 2 cross 2 plane is the example of a Cartesian. Now, when I look into this Cartesian plane, or when I'm looking into this Cartesian plane, so I need to first understand what are its properties, right? So what are the things that this Cartesian plane has, or what are the properties of this Cartesian plane? Now once I know that property, only then will I be able to go to the state of optimization and apply it. So that is another reason why I have been saying that real analysis is the foundation of any optimization exercise, and that is why you are taught real analysis right at the beginning of the discussion, right? So it will be that foundation on which the entire optimization theory will be built. Now let's explore this further, right? So now let's start off with the properties of the Cartesian plane. This properties of the Cartesian. Properties of the Cartesian. Right. So let me let me draw another Cartesian plane over here. This is 0, this is x, this is y. Right. So now let's say that I have one point over here. I'll call this point x0. I'll call this point. Right. So I have x0 and I have y0. So this is one point over here. So let me call this point x. Right. Now I have a point over here, x1, and I have a point y1. I have this point y, right? So how is x defined over here? X in my model, or x in this case, is defined as the Cartesian product of x0 comma y0. And over here it is y is x1 comma y1. Right. So I have two of these things. Now, what is the property of this space? First of all, one of the things that you can see is that I can define a distance between these 2 points. Now, if these 2 points are there in this space, right, x is belonging to, so over here, so let me specify it further, x0, x1 belongs to real. Then you have y0, y1 belongs to real. So these are both are real numbers, right? So now if these 2 points, x and y, so let me call these points x dashed and y dashed. This is x dashed. Now these two are two Cartesian points, Cartesian products, right? Now between these 2 points in this two-dimensional space, I can always plot a distance between the 2 points, given that all these are real numbers. So the first property of this space is that given any 2 points, so when you plot this graph, right? So given these 2 points on the space, you can always draw a, or you can always capture the distance between the 2 points. So that's the first thing. So I can always calculate the distance between x dash and y dash, between any two x dash and y dash, right? I can calculate the distance between any two x dash and y dash. Any two x dash y dash. Dash belongs to real. So for any two Cartesian products or any two real Cartesian products which are plottable on the real space, it is always possible for me to calculate the distance between these 2 points. Right. Now, if I am calculating a distance, then what I can do is, or what I'll have to do is, I will have to assign a distance function, or I'll have to define a distance function. A distance function. And I'll call this function as dx, y. Now this distance function, now the way I'm calculating the distance, right? So now this function can take any form. So I may want to, I can design a specific form through which I want to calculate the distance, and that will depend on the way I want the distance, or the accuracy with which I want the distance to be calculated, the way how I would want the distance to be calculated. So that is called a distance function. Right. Now there are different kinds of distances that we can use. One of the most famous distances which you all know is the Euclidean distance. Is the Euclidean distance. Distance. Then the second distance that we have is, so after the Euclidean distance, the next distance that you generally get to see is the Manhattan distance. The Manhattan distance is a very famous distance, measure of distance. Right? You have the Manhattan distance. Now the choice of these distance functions are based on your objectives, right? The Manhattan distance. Now, similarly, you have other distances like you have the Habershine distance, which is used to calculate the nonlinear distance between 2 points. So mainly for geographical location, you use distance between two geographical locations on a plane. You use a Habershine distance, right? Euclidean distance is most commonly used, and even more commonly used is the Manhattan distance. So I can always so the basic point. Now we'll explore the distance functions later, right? But for the time being, you can see that I have so for this space to exist first, right? I must be able to plot only 2 points, and I must be able to calculate the distance between the 2 points, right? Now, if I'm able to calculate the distance, then the distance must have certain characteristics. What is the first and the most basic characteristics that a distance must exhibit? The first and the most important characteristic which a distance function should, the distance between 2 points or any function which helps us capture the distance between 2 points must exhibit is number one, the distance between the 2 points must be equal to greater than equal to 0. The distance between any 2 points. So either so if these 2 points are overlapping with each other, the distance between the two should be 0. And if there is a difference between the 2 points, then the distance should be greater than 0. So the distance must be greater than equal to 0. So if I am plotting a distance function, then this distance function, and if the space is a real space, right? If I'm trying to plot a calculate distance function on a space, that distance function must only be greater than equal to 0 for all xy belongs to real. So for all the xy which has for all real values of x and y, the distance must be greater than equal to 0. Now, what it implies essentially is that it is only that the difference, the value which matters. The direction of the distance does not matter. So that is what it says that therefore this distance is a scalar. It does not have a sign attached with it, so it's not a vector. We are trying to look into the scalar distance between the two. So that's one very important characteristic, that I must be able to plot a scalar distance function. Now, if I define a function, but how do I know that it's a distance function? The first and the most important characteristic is that it must only be greater than equal to 0, implying that it's a scalar, not a vector. Right. So the next part is dxy. The distance between x and y should be the same as the distance between y and x. So it says that the distance between x and y and y and x should be the same. So it should not be that the sign is not considered. So these two conditions ensure together that the distance function that we are trying to create, or that we have that we are looking into, or when we look into this, is a scalar. It is not a vector. So we look into that dxy is a scalar. So dxy is scalar, not a vector. Right. Now the third and the most important point is that if there is a distance function, it says that okay, if I bring in a third point into the story, right? So there should be a distance between this point and then from here to this. And let me call this point the Z. So it says that yeah, so it says that the difference between the distance between x and z is less than equal to the distance between xy. Y. Sorry, I made a mistake. This says that the distance between xy less than equal to dxz plus dzy or something like this. So I need to check the triangle inequality condition. But the entire idea is that the distance from x to y is less than equal to the distance from x to z and z to y. Right. So that's a triangle inequality. Now, if you have a distance function and you have three distinct points, then this relationship must hold. Now the question is, that if these three conditions are holding, right? So, what does this mean actually to us, and how do I interpret this part? So it says that I'm just using a plane. So the plane must exist, right? The plane must be a real plane existing over there. Now, if there is a plane and there are three distinct points, then I should be, and if it's a real point, if these 3 points are obtained from the real variable, then I should be able to the most basic requirement is that I should be able to complete calculate the distance between the 3 points or between the 2 points. And if I'm doing that, that distance must be having certain characteristics. If those characteristics are satisfied, what it means is that this plane, the space where I'm trying to plot all graphs and everything going forward, is a complete space, right? So it is a continuous space, and it's a real space, and I can plot any real values anywhere in this space. So there are no holes or discontinuity in this space. So this this is a space where I can define a metric. So I can define any metric, I can define any distances, and hence a space which satisfies these three criteria, right, is called a metric space. This is what is called a metric space. This is what is called a metric space. Now that this is a metric space, right? Now, so the first thing that I need to understand is that the space on which I'm trying to plot anything, or I'm trying to develop my whole optimization superstructure, is a metric space. So this matrix of this space of this two quadrant space being a metric space is just a very basic necessity, right, for uh, for for the model to be developed on this. That is the reason where, this is where, your real analysis comes into play. So your real analysis explores or describes the characteristics of the space on which you want to develop your model, right? And that is what is metric. And that is where, that is where we define the space to be a metric space. And given that xy space, this Cartesian space, is a metric space, then we move on to the other properties of this space. So the fact that it has to be a matrix space is a very, very basic requirement for a stochastic for any optimization problem to be developed on this space. And that is where your real analysis concepts come into place, right? So I'll take a pause over here and I'll take up if there are questions, if any. So go through this part. So think about this for a minute, right? See what you have not understood and put the questions on the chat box. I'll just go on mute. Okay. So I have three questions from Ornov and Urjit. I'll take them up one by one. Excuse me. Okay, so the first question that Urjit has is that is the whole Cartesian plane, that is the XY quadrant, a metric space, or is it only the plane that lies between x dash and y dash a metric space? No, Urjit. When I talk about a space, right, I am talking about the entire space over here, right? So that entire, so anything and everything which is lying between x and y. So x dash and y dash are 2 points, right? So x dash and y dash are 2 points. Yeah. So if I talk about x dash and y dash, so these are just 2 points that I'm using to illustrate the concept of a distance, right? So when I talk about space, so space is what? Space is this entire area, right? This entire area. So this space is between 0 to so for y belonging to 0 to infinity and x belonging to 0 to infinity, because I have defined it in terms of the positive quadrant. Now the question that comes up over here is that are the negative quadrants also included in this metric space? Definitely yes. Even the negative quadrant would also be satisfying these properties, but because it's a because we are focusing on economic variables, we don't have chances of being having negative variables until and unless they are growth rates. And since we are not talking about growth rates, we are just talking about real commodities. Therefore, this is a positive. So therefore, only the positive quadrant will be considered. Right? We'll not be considering the negative quadrants in our discussions. So when you talk about a space, Urjit and guys, always remember that it is going to be it's always this whole space, this whole area in between these intervals, which is defined as the space. You do not define a space between any 2 points. The 2 points are a points which belong to this entire space, right? Okay. Okay. So coming to the questions of Orno. The first question that Ornov has over here is, are we getting the distance between x and y or x and y? We are calculating the distance between these 2 points, x dashed and y dashed. The coordinates of x dashed and y dashed are x0, y0 and x1, y1 respectively, right? So we are always considered, so we will always be considered whenever we are talking about distance, we are coming to the distance between x and y, right? So between any 2 points, x dash, y dash, x, y, or whatever. So these are 2 points between which we are trying to find the distance. You are trying to find the distance between these 2 points, and these dashed points are, and these dashed lines are nothing but they are just representations to map the points, right? So it's nothing of the sort. It's just a matter of representation. It is not a specification of the space, right? So don't think that these dashed lines are there in the distance function or something, but this red straight line is shown to map, and this straight line is shown to create an intersection of the point, because x dashed is the point on the space which is x0 and the intersection of x0 and y0, right? So similarly, y dash is the point of intersection of x1 and y1, and the straight line between the and this dotted lines show the distance between the two, right? So I'm just trying to represent the distance, right? And it has nothing to do with the specifications of the real space. So the entire area in this part is the real space. So the next question that Arnob has is that why, so we don't consider the negative part as the space. Yes or no? For our discussions, for discussion of economics, for real space in economics, we don't need to consider the negative space, because we are considering, or because we are talking about level values, or we're talking about units of commodities, we're talking about units of income, we're talking about price units. So which are nothing but, or which is nothing but uh, your positive values, right? So they are purely positive in nature. So therefore I would not require a negative values over here. So that is why the negative space is outside consideration. However, if you, as a general mathematical exercise, if you extend this to a negative space and you try to perform the same functions, you will see that yes, the distance, the same properties of the distance functions also applying to the other quadrants as well. Right? Make sense? Okay. Now coming to Shraman's question. The Shraman is asking that I have created a optimization example over here, I mean, which we are currently discussing. But how do we then identify that this is a static optimization exercise? How do we do that? The way we do that is, the way we would do that is the following. If it was a dynamic optimization exercise, the utility function, the objective function would not have only been a function of x and y. It would have been a function of x, y, and t. So time will be a very active determinant in the objective function, in the maximization or minimization a, of the objective function. So if your objective function contains time as a as a very active determinant, then you know that yes, that is a dynamic optimization. But because over here time is not an exogenous component, right? We can say that this is not a dynamic optimization, right? Okay. So Urjit has a question over here. The why we need a Cartesian plane. So Urjit, if you have to draw, I mean, if you have to perform any optimization exercise, right, you need to define the constant functions, right? You need to define the objective function, and for that, you need a graph. You need to plot it on a graph, on a two-dimensional graph, right? So the space on which you are plotting, so this x-axis and the y-axis that you create and you plot, that itself is the Cartesian plane. So you need that space, that well-defined that space for the optimization exercise to be performed. So if I am choosing an x which is greater than equal to 0, so I need to have a line from where I am choosing that, right? So I need to have an axis. When you put these two axes together, the space which is enclosed in between is your Cartesian plane, right? Without having that plane, you cannot initiate any modern specification, because that space is where all your variables are defined. That is why you need this Cartesian plane to perform this optimization exercise, right? Arnav, Shomon, Urjit, Shreyasha, everyone, any other questions? So clarify each and every of your little doubts. Okay. So on our the question, should it be dx dash comma y dash? Yes, it should be dx dash comma y dash, where x dash and y dash are two specific points. When I write small x and small y, it refers to any generic point xy. So if you follow this notation or note that I have written, it says dxy greater than equal to 0 for all xy belongs to the real space. Now, out of that, x dash and y dash are two points which satisfies this criteria, right? So when you are actually solving it for two specific points, yes, you can always write it as dx dash. So if you write solve it for these two specific points, you should write dx dash comma y. Okay. The question that Urjit now has is, now this is an interesting question. What if we did not have a commodity bundle and only one single commodity, and he had to maximize his consumption given my total when I get, you would need not, yes, we would still need a plane because there would still be two things, right? So number one, I would have on the x-axis I would have that commodity, and on the y-axis I will have the utility from the commodity. So then that reduces the single variable function. Over here, the case that I'm actually we are talking about is a three-dimensional space, right? So we have the utility, we have the x, and we have the y. So it's a three-dimensional plane, right? Which I am kind of subjugating one axis and I'm converting it into a two-axis problem, right? That is why you do your indifference curve analysis, where you hold the level of utility as given to reduce that, to remove the utility axis, and for all that given utility, you plot all the bundles. So we'll come to that. But over here, if you have a single commodity and you have the utility function, then again that's two axes. So one is x, the other is utility from x, right? So if you plot the two, what you will have is you have your x and you have your utility from x, right? So what you will have is this particular. So on x-axis you will have your x, and on your y-axis you will have your utility from x. So therefore, yes, you again need two axes. So to do any optimization exercise problems, you would at least need a minimum of two axis planes. Now that dimension keeps on increasing as the number of commodities will increase, as the utility will, as the target variable is there, and there are a number of as the vector is increasing, and so on. So when the number of dimensions increase, right? Now we generally use a two-dimensional, or we use a two commodity model, so that representation becomes easier, because to plot a three-dimensional axis or a four-dimensional axis in a two-dimensional board space is very difficult. So that is why uh, we always restrict our analysis to a two commodity world, right? Urjit? Shomon, Shreyasha, any questions? Okay, great. Okay, fine. Okay, fine. So let's move to the next part. So now this concept of metric space is clear, right? Okay. Now that we have the metric space in place, right? Uh, how do we move forward? So now I have this. So one thing that I have seen is that in order to develop this model or to for this optimization exercise, I need to have this metric space, right? Now the question is, how does this metric space help me in framing the problem, framing that optimization problem? So let's have a look into that. Now the first thing that I have over here is this. So first I need to plot this particular objective function, right? I need to plot this objective function. So what is this objective function? Max u equal to uxy. So the first thing, so that objective function is nothing but the selfish incentive which the individual is trying to maximize or minimize. Objective function. Now, what is this objective function? The objective function is the selfish incentive that the individual is trying to optimize. Selfish incentive. Now, what is the selfish incentive? For producers, it is profits. For producers, it is profits. For producers, it is profits. For consumers, it is utility. And I'm just considering it from the maximization perspective only. I'm not talking about the minimization exercises. The utility. Right. So this is what you would have over here. Now let me think about it in some other ways. Now I want to maximize my utility, right? Now if I want to maximize my utility, there are three axes that this objective function has. So first is the utility axis, the tara dependent variable axis, and the other two axes are the commodities of x and y. Now before we go to plot this function, right? So there are some what should I say? So there are some assumptions or some necessary conditions which this utility function must satisfy. And when I go to optimize this, right? Before I go to optimize this, I need to ensure that before I'm constructing this function, I need to ensure that all those necessary conditions are quite taken care of. Right? So how does that happen? So what are the key assumptions that the utility function must satisfy? Well, what are the key assumptions of a utility function? This is your microeconomics graduation stuff. So take a minute's time, think about it, and let's list it. Right? I'll be on mute. Once I get your response, we'll get started again. Okay. So one of the point that Arnav has made 2 points or has suggested two required assumptions. One of them is the axiomatic. So one of them is more is better. The second is axiomatic. The third is average is better than extremes. Now, more is better is fine. That's a monotonic assumption. The second is average is better than extreme. That's the convexity assumption. But the second one, axiomatic. Now axiomatic is not really clear, right? Because both more and better than less and average better than extremes are axioms. Others, Okay, so someone says transitivity and reflexivity. Okay, something else? Law of diminishing marginal utility holds that is applicable for the single variable case, but not for the two variable case because we don't assume additive preferences. Anything else, Shreyasha? Okay. So the utility function uh, has a few types of. So there are a few important types of characteristics. Now there are two broad groups of criteria. One of them is the rationality criteria, or the rationality requirements. The rationality criteria, or we call it the rationality axioms. Right. Now the next part is your satiability axioms. So whether you are satiated or you are non-satiated, etc. Satiability axioms. Or satiability axioms. Right. And the third is your averages are preferred to extremes, right? Or that you would always enjoy a whole combination. You prefer variety in your life, right? The third is your convexity axioms. Now, these are the three broad exercises, right, that we generally look into. Three broad criteria, the three broad types of assumptions that we look into for the utility functions. The convexity axioms. Excuse me. Now, what are the rationality axioms? Now, within the rationality axioms, there are a few important axioms. First is the axiom of completeness. Axiom of completeness. So, what is the second one that we have over here? So, once I talk about completeness, the second is transitivity. Now, transitivity and completeness together ensures the reflexivity. So there is nothing called separately. There is nothing called a reflexivity axiom. The reflexivity axiom is a byproduct of the completeness and the transitivity axioms. Right? And completeness and transitivity together ensures the continuity of the preferences. The continuity of the preferences. Right? The next is the satiability axioms, and there are two things. One is the monotonicity of preferences. The monotonicity of preferences. The other is local non-saturation. The local non-saturation. So we have completeness, transitivity, we have continuity, we have monotonicity, we have local non-saturation. So these are a few important things. So we have the rationality axioms, we have the satiability axioms, and we have the convexity axioms. And obviously the convexity axiom is the convexity assumption. Now, these are some of the uh, these are some of the assumptions which must be there in the utility function. So before you try and optimize the function, or before you enter into the optimization exercise, when you construct the utility function, right, so some of the most important assumptions that we need to, so one of the most important exercise will be to check whether all these assumptions or these assumptions are there in that function or not. Now, to test that mathematically, again, you would need the concepts of real analysis, right? So if you remember, you would see that in your module when you were doing the classes, right, when you did your classes, you would see that you had done reflexivity, you had talked about transitivity under real analysis, and and there was a section on relations and functions, right? So that is the portion which you need over here in this exercise to validate whether all the assumptions that is mentioned in the theory is present in the function. Because if those assumptions are not present, if all those assumptions cannot be mathematically proved, then you cannot go ahead with the optimization process as is, and so as is described in, or as is described in the static optimization frameworks. So then there has to be some other changes. So that is what you need to understand, right? So in order to validate whether those properties of the assumption is there in this particular graph or in this particular function, this is where we need to understand this. So this is where we need real analysis to help us mathematically test for each of these properties, right? Because always remember that whenever in any mathematical form has or a mathematical function has assumptions, so assumptions are nothing but necessary conditions, and you need to validate each one of them before you go ahead with certain mathematical optimization, because the effectiveness of a mathematical optimization method lies on the satisfaction of those assumptions, right? So that is something that we need to understand. Okay, so any questions up to this point? Okay, so Arnav wants to understand to refresh, wants me to refresh the assumptions of completeness and transitivity. I'll come it. I'm coming to that. Okay. Before I move on, one quick question. So, is this flow and the speed okay for you guys? If you think that I am going on fast, just stop me. Okay. So before I move on, and before we try to, check whether or to try kind of, so before we try to put these results in place, and we try to validate whether the properties, and then before try to see how do we use real analysis to validate these characteristics of an optimization problem. So let us first of all try to create a functional form for the utility function. Right, I will use the most simplest mathematical representation, which we call the Cobb-Douglas production function, or the Cobb-Douglas utility function. The Cobb-Douglas production function. So the utility is u x y, right? So x greater than 0, y greater than 0. Now, this is the simplest form of the Cobb-Douglas production function. Right? Now, the first and the most important thing is that when you have a two-dimensional or a two-variable function, it means the utility is the third axis, right? And in such a case, we need to solve this problem of the third axis because we cannot represent it on the pen, or it's very difficult representing a three-dimensional axis on pen and paper. The question that comes out over here is, how do we do that? Now, how do we solve the problem of the third axis associated with the utility function? Any idea, guys? How do you solve this problem of the third axis? Okay, so Shreyas says indifference curve. Absolutely. So we have an indifference curve. So basically, with the indifference curve axis, you are holding, you choose a value of the utility from that axis, and corresponding to that, you plot multiple combinations of x and y, right? So as you do it for all the values, so you are actually reducing down the same value, or you are actually reducing that third axis. So if there are 100 different values, you are plotting 100 different curves over here with multiple combinations of x and y such that it adds up to that utility function, that level of utility. So indifference curves help us solve that problem. But while you create indifference curve, right? While you create an indifference curve and you are plotting an indifference curve on this Cartesian plane, the Cartesian plane also undergoes a certain change in the characteristic. So it no more remains a metric space. It becomes a pseudometric space. So as you implement indifference curve into the space, right, the property of this space changes, of this Cartesian plane changes from being a metric space to being a pseudometric space. Okay, so so let's try to see this graphically. Okay, yes, okay. So Urjit and Orno wants me to re-explain the concept of pseudometric space. I'm coming to that. I'm just explaining that. Okay, so let's say this is, so I'm just drawing the three axes. Okay. Okay, so over here you have the zero axis, the zero. You have the x-axis, which has the x commodity. This is the y commodity, and this is your utility, right? But now think about the fact that if you are trying to plot, so now if you are trying to plot this three-dimensional axis, what do you do? Now, plotting this three-dimensional axis is not always possible, right? Because you choose a x from here, you choose a y from here, right? So given this x and y, the x and y, right? What you do is you pull the utility function over here. So if I draw this line, so something like this is how your space would look like, right? So you have the x, you have the y, and you map the two together, and you have this. So this is your space. Now, understanding or interpreting the space is very difficult because it's a three-dimensional figure, and we are always used to seeing two-dimensional figures, right? So we need to find a way out for that. We need to solve this problem. That is why what we would do is we would change this perspective to a two-dimensional graph. So you have x, you have, right. Now what I'll do is I will take, let's say, this value of the utility, right? And I'll fix this level of utility, and I will say, okay, I'll choose all combinations of x and y such that utility is equal to a specific value. So let's say I'll do this. U bar is equal to x dot. So I will be choosing out all possible values of x and y such that this is equal to u bar, right? So let's say ur is 100. So then I'll choose 100, 0, 0, 100, 50, 2, 2, 50, 100 comma 1, 1 comma 100, 10 cross 10, then 5 into 20, 20 into 5, 3 into 33.33, 33.33 comma 3. So like this, all combinations, all possible combinations of x and y, which will give me that level of utility 100, right? So what with that, what I can do is I will plot a curve. What will be the shape of this curve? So you can see that this is x dot y equals to u bar, which is a constant. So if I have a plot of the form x dot y equal to c, then that plot is nothing but a rectangular hyperbola. That is a rectangular hyperbola. That's a rectangular hyperbola. The rectangular hyperbola. This graph will look something like this. So this is corresponding to the utility level u bar. Now let's say I choose another utility level. Like this, I choose all the distinct utility levels which are here, right? And for each of them, I plot the combinations of x and y. So what will happen? So ultimately, this axis will get removed from the graph, and you'll only be left with a two-dimensional axis, where you have multiple types of right. So like this. Now this space. So initially, which was your consumption space. So this space initially that we saw, the one that we talked about, the matrix space that we constructed was what? Your consumption space. So that was the set of all the possible consumption bundles which you had, right? Which was accessible to. Now you have all the, now this space is converted to a space of indifference curve. Now this space goes through some difference. So some properties have changed in this space. So this space is no more a pure metric space. Can you tell me why? What has changed in this space? Or something has changed in this space. What has changed? Okay. So Arnav, has a question over here, that is metric space and Cartesian plane the same. So a Cartesian plane is the plane, right? And that on that Cartesian plane, it is possible to define a metric, right? Which can help us capture the distance between 2 points. So that is why a Cartesian plane is a metric space. But it does not always, so all metric spaces are Cartesian planes. But all Cartesian planes need not necessarily be metric spaces. And with the indifference curve, this criteria comes in very handy. Now, one very default properties of so one property of this So one property of this matrix space is that dxy is equals to dyx whenever x is equal to y. So for all, so whenever x and y is the same, right? Sorry. So one very trivial property of the matrix space is that these dxy is equal to 0. So when for all x equals to y. So whenever x is equal to y, right? So whenever let's say x and y are the same points, then the dxy is equal to 0, right? So this is a very trivial property, but it is also a very critical property as well. Now let us check for all these properties over here in this space. So let's say this is point x over here, and this is point y over here. Now, now is it possible for me to define a function which will capture the distance between these 2 points? Yes, I can always define a dxy which will capture the distance between these 2 points. So the first property is ticked over here. Now, if the distance from x to y, whatever the distance between from x to y is, the same will be the distance from y to x. The second property is ticked over here. Now let's say I have the third property over here. I have the third point z over here, right? So then dxz, this distance plus this distance less than equal to this distance, right? So this third property also holds. Now come to the last property. Now it says that dxy is equal to 0 for all x equals to y. So if x and y is the same, right, then the distance between x and y is 0. But now let's say x and y is not the same. So let me plot x dashed over here, right? So that what is, so the utility from x is u bar, the utility from x dashed is u bar, right? So the distance between the two is 0. But observe that x and y, x and x dash are lying on the same indifference curve, but they are two different points. So in this case, your dxy equal to 0 for all, only for all x equals to y is violated. So in this space, right, in this space, all properties but one is satisfied. So therefore, this space of indifference curve, or the indifference curve space, or a level curve space, is a pseudometric space. It is not a metric space. So while your consumption set or your production sets are metric spaces, your isoquant space or your indifference curve space are pseudometric spaces. This is where your real analysis comes in to justify your, or this is how your understanding of real analysis or your concepts of real analysis is going to impact your optimization models. Am I clear on this part now? So this metric space or this utility space is your pseudometric space. This is a pseudo metric space. Okay, so just so once more. Now you can see that the matrix space has four properties, right? Now all the first three properties also gets satisfied over here for this indifference curve space. But what does the last property tell us? It tells us that the distance between x and y is zero when x is equal to y. Now observe these 2 points, x and x dashed. The utility from x is what? U bar. The utility from x dashed is what? U bar. Right? So what is the difference between the two? So now if I calculate the distance between x and x dash, what is it? Distance between x and x dashed is what? Zero, right? But that does not necessarily mean that x and x dash is the same point. The vectors are two different vectors, but they lie on the same level path. That is the reason why this space is called the pseudometric space. Right? So if x is equal to y, then the difference is zero. When the distance is zero. But if the distance is zero, that does not necessarily mean that x and xy is the same. So this property, the last property dxy equal to 0, even only if x equals to y, is violated over here. So if x equals to y, then it is distance is 0. But if the distance is 0, that does not always mean that the difference is 1. I mean the distance is 0. I mean that does not mean that x equals to y. Right? Clear on this part? Clear now? Okay, fine. So over here, one thing that we see is that when you are trying to construct the problem, so now what we have done is we have constructed the indifference curve and we have seen how the property of this space has changed, right? Now the next question is I need to validate that each of these properties of uh, the utility function is there in this objective function so that I can actually use this as an objective function for mathematical optimization, right? So that's the next set of steps, next set where your real analysis comes into play, right? In static optimization exercise. So let's take a pause here for the day. We have covered quite a bit of it, right? And I'm pretty sure it's new to you. So you would need to go through these videos. So I'll share this video link, the download video link with you guys, and you can download the video from there and you can go through it. So the next class when we meet, we'll start on from this point. We'll see for each of these cases that how is it that this optimization, that real analysis can be used to classify each of the or to validate the properties of the functions, each of the properties of the functions. And from there, what I'll do is we'll start optimization. So we'll see how the next steps of real analysis. So how does static optimization and real analysis, gets interconnected with each other? So that is the next part that we'll do, right? So by the end of the next class, we will I plan to develop a clear understanding of how each of these topics are intertwined with each other. Then we'll take up each one of them, right? So it's more important to understand where is the reflexivity used, how is it used, where are you using metric spaces, where does open ball come into play, what are the assumptions that you use. So like this, for utility function, we need to do that. We need to do that same validation for the budget line, for the linear function, linear constant function. And then from there we go on to the optimization exercise, right? So this use case will give you the foundation of all the required behavior, of all the required concepts that you need to study your optimization and your real analysis. And from there we'll take up each of the topics and delve deeper in. Right? Make sense? Perfect. So thank you guys. Thank you for your time. Thank you for patiently sitting through the session. And we meet tomorrow at around 8:30. I'll be sharing the link. We'll meet for the econometrics class. All of you can attend the sessions. Thank you.